In the previous video, we explained about the general construction sequence of Habitat 67, which areas had concentrated piles installed, which cranes were used to move the modules into their designated positions, how the modules were supported stably without underlying structures or top modules, and about the clusters that consist of 4 levels with 2 modules on each level. In this video, we will delve deeper into the topics discussed in the previous video mentioned earlier. We will explore where the piles were actually placed, the movement paths of the cranes, the methods used to lift heavy modules stably, and the considerations taken during the stacking process of the modules. Habitat 67 is constructed on an artificial landmass created for Expo 67, which means the ground is weaker than other areas. Therefore, it was necessary to effectively drive piles to distribute the load of Habitat 67. When dividing the structure that distributes the load of Habitat 67, it can be broadly categorized into box clusters, horizontal street girders, vertical elevator towers, and columns. A total of 1,120 piles were used in Habitat 67, with 3 to 4 piles in each pile cap. The length of each pile was approximately 6 meters. These pile caps were concentrated in areas where large vertical loads were applied, such as vertical elevator towers, columns, and the bottom box clusters. You can see this clearly in the modeling file you are currently viewing. In the drawings, you can also double-check that the piles are concentrated under the vertical elevator towers, columns, and the bottom box clusters, which bear the largest vertical loads among these structures. Now, let's explore the various types of cranes used in Habitat 67 and how they lifted the module safely and efficiently to complete the construction of Habitat 67. The construction of Habitat 67 required various types of cranes such as gantry, derrick crane to transport and lift the precast modules into place. The movement paths of the crane were primarily located along the St. Lawrence River, providing an efficient route for transporting precast modules from the plant yard to the construction site. Once the modules were completed, the gantry crane moved them to their designated positions on the construction site. This allowed the derrick crane to lift the modules to higher locations as needed. The lifting process was facilitated by an adjustable cylinder, which created a flexible frame for precise lifting and maneuvering. Typically, the lifting process would involve directly attaching straps or slings to the object, allowing for flexibility through the adjustable trolley. However, in the case of Habitat 67, since all the modules were identical in size, there was no need for adjustable trolley with flexible positioning rails. This approach is similar to using a modular spreader frame, providing an efficient and consistent lifting mechanism. The crane lifting frame module connection was achieved by attaching steel chains or straps to the lower part of the frame. These chains were equipped with hooks that were used to connect the frame to the module. This method ensured a secure lift and precise placement of modules into their designated positions. The use of hooks provided flexibility and ease of attachment, contributing to the overall efficiency and safety of the construction process. The combination of crane types, movement paths, and lifting methods enabled the construction team to efficiently and accurately assemble the modules. This ensured the stability and quality of Habitat 67 throughout the construction process and demonstrated the successful application of innovative construction techniques. In previous presentations, we've noted that Habitat 67's modules are not stacked in a straight line but pop out in various directions. Normally, stacking modules directly on top of one another or without a supporting substructure would lead to instability and collapse. However, in the construction of Habitat 67, no substructures were installed, nor were modules stacked directly on top of each other immediately. Instead, an L-shaped arrangement was used on each floor, where 2 modules were placed side by side and 2 more modules were stacked on top in a similar configuration. This method allowed for stable stacking without the need for substructures or counterbalancing forces from above. Photos from the construction process confirm the stable positioning of modules without additional support. However, as repeatedly mentioned in previous presentations, each dwelling in Habitat 67 is composed of at least 2 modules and up to 4 or 5 modules. If all the walls of the modules were closed and not perforated, it would be impossible for residents to move physically between modules. Therefore, the modules used in Habitat 67 had their walls perforated to match their designated positions before being lifted by the crane. The walls were not only perforated for paths between modules, but also to accommodate entrances and windows according to the designed locations of each module. The ceilings followed a similar approach. All modules of Habitat 67 were lifted without ceilings. Once the modules were stacked in their designated locations, the corresponding ceilings were assembled on top of the modules. This approach also included perforating the walls in advance for the installation of stairs in places where interfloor movement was required, as there were both single-story and two-story units in Habitat 67. The stairs connecting lower and upper modules were not made of concrete. Instead, they were prefabricated stairs designed for easy installation. Assembling the ceilings later offered various advantages. Firstly, it allowed for easier access to the hooks used for lifting the modules with the crane. Additionally, since the weight of the ceiling was not initially present, the crane had less load to lift, reducing its overall burden. The most fascinating aspect from a structural perspective was the arrangement of the prefabricated modules into clusters. Each cluster consisted of 8 boxes with 2 on each level, forming an L-shaped configuration. These 4-story box clusters were interconnected with post-tension cables, resulting in a single cohesive structure. The L-shaped arrangement was defined in space, with each subsequent level created by rotating the lower module 180 degrees. This process was repeated to construct each successive level. The roof of the level served as terrace space for the upper levels. Subsequent levels were created by mirroring the lower module and then rotating it 90 degrees. This method of construction resulted in various terraces due to the differing configurations. When stacking the modules, walls in the ceilings or floors were pre-perforated to accommodate duplex units, allowing for interfloor movement within these units. Finally, let's briefly examine the elevator cores and pedestrian street cores, which we will be explored in more detail in the next video. Habitat 67's construction process focused on the elevator cores and pedestrian streets, with the clusters of prefabricated modules interconnected both vertically and horizontally. The clusters were fastened to the horizontal street girders, located at levels 5 and 9, which were supported by vertical towers and columns. The clusters and street girders were inclined about 60 degrees relative to one another, providing structural integrity. This configuration allowed for the stacking of the 3 clusters of boxes, which were tied vertically to each other and horizontally to the street girders. The construction sequence began with the installation of piles, followed by the installation of passages between the first floor clusters. Then, the elevator cores were constructed from the first to fourth floors. The fifth floor saw the installation of the horizontal pedestrian street, connecting the clusters and cores. Next, the cores were built up to the 8th floor. The 9th floor featured the installation of another horizontal pedestrian street, further tying the structure together. Finally, the elevator cores were completed up to the 12th floor, establishing the foundation for the unique design and layout of Habitat 67. Interestingly, the explanation for the stability of the modules that we have discussed so far applies to those modules that are all located far from the elevator cores and pedestrian streets. The modules placed close to the elevator cores and pedestrian streets were stacked by distributing the load directly to the elevator cores and pedestrian streets or by installing supporting columns underneath rather than relying on more complex engineering designs. In today's video, we examine the locations where piles were concentrated and the movement paths of the cranes based on a 3D modeling file. We also took a closer look at how the crane lifted the modules stably and explored the installation of the elevator core and pedestrian street core, which form the framework of Habitat 67. Additionally, we delve into the clusters covered in the previous video in more detail and learned about the considerations taken during the stacking of the modules. In the next video, we will delve into whether the grooves on the modules were solely for structural stability or also solved to accommodate wiring and utilities. Additionally, we will explore how the clusters we discussed today transfer loads to the horizontal street girders and how these girders, in turn, distribute the load to the vertical elevator towers and columns. We will also explain why Habitat 67 resembles a pyramid with modules arranged wider at the base and narrowing as they ascend. Thank you very much for listening to our Team 7 presentation.